This is Josh White with JW Math Tutoring. In today's video, I'm going to go through and show you all the methods and techniques you can use to solve for a constant in a system of linear equations problem. So let's go ahead and get right to it.
But life is a dream the calculus could never predict.
Welcome back to the next installment of my ultimate Desmos guide to digital SAT math. In this video, I'm going to go through and summarize some of the different options you have available to solve for the value of a constant or constants in a system of linear equations. So I'm talking about problems where they give you two linear equations, they tell you that the system has either no solution or an infinite number of solutions, and then they ask you for the value of one constant, or sometimes they'll ask you for the ratio of two constants. So it might say like P over R or G over K or whatever. So there's multiple different methods that you can use. What I'm going to do is basically do one example problem through and solve it. I'm going to use each of the four different methods and just briefly talk about all of them. And then after that, just give kind of like a brief overview, brief summary of the advantages and disadvantages to each of the methods. So a couple things just to be aware of. First, this sheet will be made available as a separate PDF file that you can download. Link in the description and in the pinned comment. However, everything that's listed on here is, at least on this first page, is also on the main guide. So the ratio method, that was covered in a previous video. I'll put a link in the description for the specific one. I forget exactly which part it was. The slope intercept, or SI form method as I call it, was also covered again in a previous video, and I'll put a link in pinned comment in the description for the video where that was covered. Now for the two other methods below, which are very, very similar. The first one was covered basically in the previous or the last video. The one below that, basically method 2, has not been covered. So this one is actually brand new and will be shown, essentially for the first time in this video. But the other three have been covered already in videos. So if you are familiar with them already, then you don't necessarily need to watch the actual solving of the problems of them. You can probably just skip to watching the one new method and then also the summary at the end. All right, of course, if you like this video, please do give it a thumbs up, subscribe to my channel, and sign up for notifications. So let's go ahead and get started. All right, so the first method that I have listed here, I call it the ratio method. And typically, when you're going to use this, you will need the equations to be in standard form. Now, one caveat just to get out of the way. When I say standard form, what I mean is all the x and y terms on the same side and any number or quote constant terms on the other side. Technically, they might not be in what's considered standard form because the technical definition of standard form is no fractional coefficients, and also the coefficient on the x term being positive. All right? But that might not be the case. I'm using the term standard form to mean all x and y terms on the same side and all number terms on the other side. So just to to make sure everyone's aware, it's not the same textbook definition of standard form that you would see in an Algebra 1 or Algebra 2 book. Okay. So anyways, the ratio method. Basically, what you do is you get both equations into, again, quote, standard form, and then you do a ratio of the coefficients. And the way that I like to do it is put the x coefficient from the top over the x coefficient from the bottom, and then the y coefficient from the top over the y coefficient from the bottom. Now, you can use this method to solve also for the basically for a constant term or for a number term. In other words, if just there's a number term in the problem and it just has a letter for it, it's really a constant that you're solving for, you can do that as well. You can do the ratio of the constants as well. So let's see exactly how it would work for this specific problem. So this is the problem that I'm going to be working through using each of the four methods. It is 2/3 x minus 1/7 y equals 4/3. That's the first equation. Second equation is py equals 3/2 x minus 3. And we want to find the value of p such that this system of equations has an infinite number of solutions. All right, so what you need to do for this method is to get the x and y terms on the same side. Okay, in the top term, that is already done, so you don't need to do any work. However, in the bottom equation, not term, top equation. In the bottom equation, that is not done. So you either need to move the x over to the left, or technically you need to subtract the y over to the right. It doesn't matter which one you do. So I'm going to move the x, basically over to the left. So that would turn this bottom equation into negative 3/2 x plus py equals negative 3. All right, so now I have it set up into, again, modified standard form. And so all I'm going to do is basically go to Desmos. And again, I'm going to do ratio of x coefficients. So 2/3 is the x coefficient from the top. I'm going to put that over negative 3/2. That's the x coefficient from the bottom. Then I do a regression. Then I do, for the y terms, ratio from the top, negative 1/7. And then ratio from the bottom, that would just be p. All right, so it has solved this for p. Let's see what p is. Okay, it's this decimal, so you could type it in as 0.321. You could type it in as 0.3214. Or for the fractional form, we could also type in 9/28. Okay, 9/28. So that is the correct answer. Let's just confirm that is the correct answer. So what I'm going to need to do is I'm just going to type the first equation. I'll slide this up in 1 second. All right, so there's the first equation. Second equation, py equals 3/2 x minus 3. And notice both equations should match the exact given problem. 2/3 x minus 1/7 y equals 4/3. Check. Py equals 3/2 x minus 3. Check. Okay, and they are overlapping each other. Therefore, it is confirming its infinite number of solutions. So 9/28 is the correct answer. Okay, so just going forward for the other three methods, I'm not going to bother, graphing them all out and just confirming. We now know what the correct answer is. Okay, so actually I could probably just leave them here and then just flip them on once I find p using the other methods. All right, and now one other thing I want to show you too, related to this is, so I did x top over x bottom, y top over y bottom. Okay, p is a coefficient on a y term. So I need to leave that in. However, I could have used the constant terms as well. So what I mean by that is, instead of the x coefficients, I could have also used 4/3 and then put that over negative 3. And notice I get the exact same answer. I get 9/28 for p. Still get infinite solutions. So even though on the sheet I have like x over x and y over y, you can also use the numerical constant terms as well. Notice that is only for infinite solutions. You cannot do that for no solution. It's only for infinite solutions that you could use those as well. So please, just be aware of that. All right, so now let's go ahead and look at, let's just delete this, the second method. Let's talk about this. All right, so this is called, I call it the SI form method or slope-intercept form method. Basically, what you're going to do is you're just going to take both equations, you're going to rearrange them into slope-intercept form, so you get y equals. Then you're going to use regression to set the two things equal to each other. You will have to create a list for this. Have to set x1 equal to blah, 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 whatever. Creating an element list to tell Desmos to treat x1 as a variable, not a constant. And then you can type in, whatever thing you're looking for. So those examples on the guide are for if you had a ratio of constants, find the value of c over a or r over p. But if you have one constant, you just type in that constant and that's it. Just type p or r, c, whatever it is. You don't have to simplify or combine the terms here, okay? And you can have like multiple terms for x and or numbers and everything. Note, this method only works for infinite solutions. Basically, you're getting both into slope-intercept form, and then you're setting them equal to each other. Really, that's what you're doing. So that's obviously not going to work for no solution, because no solution, the two lines will not be equal to each other. They have the same slope, but they will not have the same y-intercepts. Therefore, you do have to do some work to get them in both the slope-intercept form, but you can actually, you can do it in your head. So here's how I would reason my way through this. Top equation, I have 4/3 on the right, okay? I'm going to subtract over a 2/3 x term, or 2/3 x1, since we're going to use regression. And then we need to divide everything by -1/7, because that's the number in front of the y. So I'm just visually thinking I move the x term over by subtraction, and then I divide by the number in front of the y. Then I use regression to set that equal to the bottom. Now this one is actually much easier, just dividing both things by p. So you could actually just type in, 3/2 x1 minus 3. That's the original equation, and then just divide everything by p. Now, this is not the correct answer, again, because I have to define a list for x1. All right, so once I add some values in there, notice I have the same p-value. It's 0.3214, blah, blah, blah. And now if I go ahead, just jump up here, let's graph the lines. Are they overlapping entirely? Yes, they are. That just confirms we have the correct p-value and we have an infinite number of solutions for this system of equations. So this is a method, again, that you can only use when it's an infinite number of solutions that you're looking for. It's not for no solution. You cannot use it for that method. All right, let's talk about the two methods at the bottom now. So these, again, are ones that you're probably going to use either first one in standard form, second one can technically be in any form. All right, so the first approach, I call it the equal zero method. Again, you're going to put both equations into modified standard form, meaning get all the x and y terms on the same side, any number constant terms on the other side. You don't have to combine them. You don't have to simplify them. You can just have multiple x and y terms on either side. And you can, in one equation, you can put everything on the left. The other, you can put everything on the right. Okay, it doesn't all have to be on the left for both equations. It could be left for one, right for the other. Then once you do that, you're going to type a regression statement, and it's basically going to be like the equation 1 left, meaning everything with the x and y terms, and then comma, and then equation 2. Now I put left here, but again, it could be the right. That part's irrelevant. The point is, you're putting all the x and y terms in the brackets there on the left side of the regression statement. Then on the right side, you're just putting 2 zeros. You're basically regressing both of them equal to 0. What that does is it forces Desmos to give essentially to give both equations the same slope, the same ratio of x to y coefficients. So let's look at how this would work in practice for this problem. So this is actually very similar to the first approach in that the first equation is already in standard form, or modified standard form. So we just start off with 2/3 x1 minus 1/7 y1. Okay, but now for the bottom one, we either have to move the y term over to the right or the x term over to the left. Okay, I am going to move the x term over to the left by subtracting it, and then plus py1. Now, I do regression, and again, I set both things equal to 0. Notice I'm having a problem here because I still have the element list defined from the previous thing, so I want to get rid of this. Okay, now it has worked out. Notice it's going to find values for x1 and y1. That's fine. You can just ignore that. That doesn't matter. That's irrelevant. That does nothing for the problem. The value of p that we get is the correct answer. You can see it right here. Hopefully you are recognizing it, since this is the third time we're going through this now. And again, the two graphs, the two lines, you graph one, you graph the other, and it is overlapping. Okay, so that just confirms we have an infinite number of solutions here. Now, let's talk about the, basically what I have here is method 2. So this one is going to be very similar, except for this, you actually don't have to move any terms around. Technically, what you're going to do is you're just going to take the equations as given, and you're going to eliminate or not type any of the constant or number terms. Okay? So what that means is, for the original problem up here, when I go to type it in, where there's a number term, I'm just not going to type anything. So in other words, this is just going to be eliminated, which means it would be really replaced with a 0. And then this would also just be eliminated and technically replaced with 0, but since there's already a term on the right, you would type nothing. All right, so here is how it will look in practice. So it's going to be, again, equation 1 left, which would be 2/3 x1 minus 1/7 y1. And then the bottom equation left here, that's just the p1y1, py1, because I didn't move any terms anywhere. Now, equation 1 right. So that's where there was I think it was 4/3, but it's no longer there, so it's now just a 0. And then for the bottom one, here's where I have to put the 3/2 x1. So notice again, it returns an x1 and y1 value. Don't worry about that. Ignore that. That doesn't matter. That's fine. The p value is what we're concerned with. And again, it is the correct value here. So notice, again, if I graph each of these, they are overlapping. Therefore, we have an infinite number of solutions again. So the main advantage to this is that you don't have to actually move any terms around. Okay, that's like the one great thing about this. However, one disadvantage, and I'll get into this a little more on the next screen, is that you will need to add a constraint if you have a constant term which is in a denominator. So what I mean by that is, if I took this and I changed it into 1 over p, okay? So everything else was the same, but I changed it to 1 over p. Basically, we would expect, so here's the p-value, right? It's 9 over 28. I would expect the p-value to be the reciprocal of that, which is 28 over 9. However, notice if I change this here to 1 over p and keep everything else the same, it's just giving me this value of p equals 1, and then when I go try to graph these, it's not infinite solutions. They're not overlapping. So what's happening or what's going on? Well, the problem is this whole x1 or y1 thing. It's just defaulting them to 0. So that's what you have to add a constraint for. So you need just to put in something like x1 is greater than 0. Now, okay, did it give us the correct value? No. And so notice the reason is because even though it technically gave us an x1 value greater than 0, it's this microscopically small, 10 to the negative 218, 218, whatever. It's functionally 0. So let me try 1. Okay, so now notice it does give me the correct expected value. So notice down here now, p is 3.1 repeating, which is 28 over 9. That's the value that I expected. Now, these are obviously not, oh, actually, yeah, I should have changed the graph here. Now you can see that they are overlapping in its infinite solutions. But again, if I get rid of this constraint here, let me just see if I can get it to yeah. So notice again here, now I have this typed down here correctly to match how I modified the problem, where I just made it 1 over p. So notice again here, they're not infinite solutions. It's not until I add that constraint and specifically make it greater than, say, 1. Now I get the correct value for p, and therefore I get infinite solutions. Okay, so that is one thing you have to remember. That is one potential downside to this method. Okay, let's go to the second page of this sheet now. So to briefly summarize these, at the top I have some different scenarios, and like there's my ranking of which method I would use or which one I would prefer to use. Notice a couple things. First of all, if you have to find the value of a number term, i.e., just a constant term, um, doesn't matter what form it's in, you can't use like the last two methods. You have to either use the ratio method or slope-intercept form method. And of course, if it was that would only apply to an infinite solution problem, as well. Now, if it's already given where both equations are already in standard form, and again, we're assuming here you're looking for x and y terms only, like the first two rows there, um, I would probably just go with the ratio method just because it's less typing than, the no constants method or the equal zero method. But, it's personal preference if you want to do one of those other ones instead. If at least one or both of the equations are not in standard form, then I would most likely choose the no constants method, just because you can type it in exactly as it is, just eliminate the constants, you don't have to move any terms around. The other methods, you have to move at least one or more terms around, and that takes work, and that takes time. All right, so now, just to quickly go through the four methods, brief summary, pros and cons. First, the ratio method. So, major pros. It works for any type of problem. No solution, infinite solution, coefficient on an x, coefficient on a y, coefficient on a, just a constant or number term, whatever you're finding. You don't need to bother typing like x1 or y1, which sometimes can take, extra time with all the subscripts and stuff. However, main con is you need to have x and y on the same side for both equations, so you may have to do some manual work, to move terms around or move terms over. Okay, the slope-intercept form method. The downsides are that it only works for infinite solution problems, can't use it for no solution problems, and also it requires solving each equation for y, which generally will require some work. However, depending on the setup of the problem, it could require less work than actually putting it into standard form. Like, this equation, the second equation in my example here, all you had to do is divide by p in order to get it into slope-intercept form. You didn't have to actually move any terms around. You just, divide by one letter and that's it. Next, we have what I call the equal zero method, where you do the regression and you have, two zeros on the right. So it works for both no solution and infinite solution cases. However, you do have to move terms around, if they're not already both on the same side. It's not in standard form, so it might require some work. It only works when finding a constant or coefficient on the x or y terms. You cannot use it to find the, the value of a number term. And if a constant is in a denominator, then you have to add a constraint normally to get the correct answer, because otherwise it defaults to x10 and y10, which messes up the p-value. All right, lastly, the no constants method. So the biggest advantage to this is that you do not need to move any terms. You just type in exactly what you're given with the equations and just replace any numbers or constants in it with 0. And it does work for both no solution and infinite solution cases. However, again, the same downsides that I just mentioned for the equal zero method, or at least two of them are the same. It only works, you can only use it to find constants that are in front of an x or a y term. You cannot use it to find the value of a number term. And again, if the constant is in a denominator like 1 over p, 2 over p, 3 over 2p, or whatever it is, then you will most likely need to add a constraint in order to get the correct answer. Okay, so hope you enjoyed this video. I just get actually one last thing on this, and then I'll do the little conclusion. So I guess I would say if you only wanted to kind of memorize and master one method, then I would pick the ratio method, because that is applicable to any situation, any type of problem. It will work. However, I do mention the other methods because, some of you might like using the other methods, might find them easier or more intuitive, in certain situations. So if you want to learn like multiple methods, again, that's fine. But if you only want to learn one method that will apply to all types of problems, you kind of like the most generalized thing, then I would recommend learning the ratio method of the coefficients. Okay, so Hope you liked this video. If you did, please do give it a thumbs up, subscribe to my channel, sign up for notifications. If you have any questions or comments or feedback, please do leave them in the comment section below. Also, if you haven't done so, check out the other videos in my Ultimate Desmos Guide to Digital SAT Math playlist. If you also haven't done so, check out the other Desmos SAT Math playlist, which basically has some select, highlighted uses of Desmos from Blue Book practice tests 1 through 10. Otherwise, good luck in preparing for the digital SAT Math exam, and I'll see you in the next video real soon.